This is another video in the Systems and Proof module for Foundations of Computer Science. We'll be looking at a proof by mutual induction of a simple property of rooted trees. And the proof is a little bit on the longer side, so I'm splitting the video into two parts. The first part will just be everything up to the inductive step, and the second part will be the inductive step. In the first part, which is this video, we'll begin with a review of the definition of rooted trees. I'll make some remarks about mutual induction in general, and then we'll move on to an overview of the proof and prove the base cases. Then in the second video, we'll just go through the inductive step and finish the proof. Okay, so let's start by reminding ourselves of the definition of rooted trees. Remember, we define these using a mutually recursive post system in which we had two sets. We have RT, and that is our set of rooted trees, and we have RTL, that is the set of all lists of rooted trees. And we begin with just one base case where we say nil, which is the empty list, is in our set of rooted tree lists. Then we have a rule R1 in which we say if X is a rooted tree and Y is in the rooted tree list, then we can add X to that list, right? We can add this rooted tree to this list of rooted trees, and we get a longer list of rooted trees. And then our rule R2 was that if we have some rooted tree list, we can use this function node to create a new rooted tree from that list, and that goes in our set of rooted trees. Remember, the idea we're trying to capture here is that to create a new rooted tree, what you do is you create a root, and then you attach that to some list of already existing rooted trees. And if that list is empty, what you get is just the root by itself. But if the list has other rooted trees in it, you connect your root to all of those, and you end up with a new rooted tree. And then, of course, once you've defined your rooted tree, you can use Rule 1 to add it to any existing rooted tree list. Then you can build a new tree from that new list, etc. So that's the basic idea we're trying to express in this post system. And remember, when I first introduced this, I made a claim that when it came time to prove some properties of rooted trees, there would be a benefit if we wrote the definition as this mutually recursive post system. So now we are introducing a property of rooted trees, and we're going to prove it. And hopefully, as we walk through the proof, our motivation for setting things up this way will become more clear. The property we're going to prove is pretty straightforward, and it is stated by the following theorem. If T is an element of the set of rooted trees, then the number of edges in T is equal to the number of nodes in T minus 1. So in other words, for all rooted trees, it is the case there's going to be one more node than edges in that tree. So before we proceed, it's probably worth convincing yourself that this statement is actually true. And to do that, let's just look at a few very simple cases. So let's just start with the smallest possible rooted tree, which is the tree that is just a node. And this has one node and no edges. So the theorem holds for this tree. And if we were to look at a slightly larger tree, every time I add another node in, I have to connect it with an edge. So I'm always adding one node and one edge here. Right? So that seems true, but the question is, how do we prove this is true for all rooted trees that we can generate, with this process we had described of taking a new node and connecting it to all of the trees in a list? The way we will prove our theorem is actually by proving two related statements. The first is a statement about rooted tree lists. And it says the number of edges in a list is equal to the number of nodes in a list minus the number of elements in the list, or in other words, the length of the list. And the second statement is just our theorem. The number of edges in a tree is equal to the number of nodes in a tree minus 1. Now, to a suspicious person, it may look like we have just doubled your work, right? Because not only now do we have to prove our theorem, we've added another statement that you have to prove. And you might wonder, well, how does that make things better? And one response to this is that it's actually not that strange when you're writing a proof of some theorem to define a lemma or some statement that you prove first and then use ultimately in your final conclusion somehow. However, In this case, what we're doing is a little bit different. We have a proof by mutual induction. And the big advantage of structuring things this way that we're going to rely on is that when we get to our inductive hypothesis, we'll get to assume both of these statements, and we'll be able to use each one to prove the other one. And so that is the fundamental characteristic that we're referring to when we talk about a mutual induction. Mutual induction is just a strategy for structuring an inductive proof. And so like other inductive proofs, you can have different varieties of it. You can have weak mutual induction or strong mutual induction, etc. And so what we're going to do here is a proof by strong mutual induction. And as usual, we have to say what we're doing induction over, and we're going to choose derivation height again, since we've gone to the trouble of setting up this post system. Now, just to make sure I don't lose anybody on notation, I will go over some of the conventions we've adopted here. I've been reading these aloud, so they're probably pretty clear, but just in case, the vertical bars around L stand for the length of the list L, and the pound sign or number sign edges means the number of edges in L, and that's true whether L is a tree or a list. The pound sign nodes L is also the number of nodes in L, and that's also true whether it's a tree or a list. And so if it happens to be a list of trees, what you would do is count up all the nodes in all of the individual trees in that list, and that would be what pound nodes or number sign nodes L means. Now, just as in our previous examples of inductive proofs, we've established some some statement that we're going to prove. And in this case, the difference is we have an S sub 1 and an S sub 2, but we're still going to do the same thing next, which is to take our parameter, which we've chosen derivation height, and parameterize this compound statement. So we have S of 1 of n now, which is if the derivation of L has height n, then the number of edges in L is equal to the number of nodes minus the length of L. And as usual, all we've done here is add a height n into this statement without really changing the meaning, because as always we know that every element derived in our post system has to have a height of some n. We do the same thing for S sub 2 of n, right? If the derivation of t has height n, then the number of edges in t is equal to the number of nodes in t minus 1. And we can, again, write this out in a sort of formal logical statement. It starts with our two base cases, S1 of 0 and S2 of 0, and then we proceed to our slightly long looking statement of our inductive hypothesis. And if we establish both of these things, then we get to our conclusion, which is that this statement n holds for all n greater than or equal to 0, which means it holds for all derivation heights, and therefore for all of the objects that we can produce from our post system. Now, before I move on to our natural language reiteration of this symbolic statement, I'd like to highlight an aspect of its structure that is especially relevant to how you understand mutual induction. I've kind of hinted previously that in a certain way of thinking, mutual induction is really just an organizing strategy for an inductive proof. And if you look at what's going on here, I think you'll see what I mean. Superficially, it looks like everything has doubled. So for example, if you look at our base case, before we might just have had S of 0, and now we have these two statements, S sub 1 and S sub 2 of 0, combined with a logical AND. If you think about that though, remember we can always write a statement with a logical AND in the middle as just a single statement, right? We could write this as just an S of 0, and it could contain in it the conjunction of these two substatements. So in other words, we could have this single statement, which is the whole thing here, starting with if the derivation of L has height n, then the number of edges in L is equal to the number of nodes in L minus the length of L, and if the derivation of t has height n, then the number of edges in t is equal to the number of nodes in t minus 1. That whole thing could be our S. And so in a sense, we have just split it entirely for our convenience, right? And it happens that this works out well because the split corresponds with the two objects in our mutually recursive definition of rooted trees. If you follow through with this kind of replacement throughout the statement, you'll see that even though it actually looks long, if we group these S sub 1 and S sub 2's together, really we have something that looks very like what we saw before with strong induction. So all we've done is sort of split a statement into two statements that are actually a logical conjunction. Because you can do that, mutual induction is always equivalent to some other form of inductive proof in which you do not split the statements. Hopefully that gives some sense of why we're allowed to do this and you don't feel like there's some kind of magic going on here. So as promised, I will now give a natural language version of our symbolic overview of this proof, and we'll start by saying, okay, the basis step, that is where we have to show our statement S sub 1 holds for n equal to 0, and S sub 2 also holds for n equal to 0. We'll do that in a moment. Next, we have the inductive hypothesis and the inductive step, and these are just as before, except they are now split into these two statements. So we suppose that our statement S sub 1 and S sub 2 hold for n equals 0 and 1, 2, etc. up to n, where n is some number greater than or equal to 0. And if it holds for all of those things, we have to show that it must hold for n plus 1. And that means showing that our statement S sub 1 holds for n plus 1, and our statement S sub 2 holds for n plus 1. So that is the overall plan, and we'll get things started by taking a look at the basis case in a moment, and we'll show that S sub 1 and S sub 2 hold for n equals 0. And then in the next video, we'll look at the inductive step and finish up the proof. Before we move on, it's just worth remembering that S sub 1 is the statement that refers to our lists of rooted trees, and S sub 2 refers to the trees themselves. And when we're talking about a height of 0, that's the derivation height of these objects in our post system. When the derivation height is 0, it severely constrains which rooted tree lists and which rooted trees we might be talking about. So when we look at rule S sub 1, if the derivation height is 0, then we're definitely talking about the empty list. And we're saying here that if the height is 0 and L is in the set of rooted tree lists, then certainly L is nil, or the empty list. And then all we have to do is say, well, does our claim hold when we're talking about the empty list? Well, the number of edges in the empty list is 0. The number of nodes in the empty list is 0. And the length of the empty list is 0. So 0 equals 0 minus 0. So that is true. Okay, so what about S sub 2? Remember, this is a statement about our tree, and we can just paste it so we remember what it says, right? It says, if the derivation height of some tree T is n, then the number of edges in that tree is equal to the number of nodes minus 1. Okay, well, n is 0 here, so what do we know about our trees that have a derivation height of 0? Well, looking at our post system, we can see there is no axiom that gives you a tree, and so therefore there is no tree with a derivation height of 0. So what does this mean for us? Well, fortunately, the way our statement is phrased is if the derivation of t has height n, then, right? So this is an implication. So that means if the antecedent is false, which we've just said it is, then the implication as a whole is true. This can seem a little bit weird, but it really just follows directly from the truth table for the implication. Remember, the implication is only false if the antecedent is true and the conclusion is false. If we know that the antecedent is false, then we know we're on the bottom two rows of this table and the implication has to be true. This might seem like a bit of a trick, but it's really not a trick. All we're saying is that our statement is not proven false when we don't even have a tree yet. In other words, since there is no tree with the derivation height of 0, our statement is vacuously true, and that is good enough to prove the base case. That takes us all the way up to the inductive step, which seems like enough for one video. In the next video, we'll pick up from where we left off and look at the inductive step and finish up the proof.